Hello everyone, I'm Woo-jin from KAIST, advised by Jay Lee, who researches about data-efficient decisions. Today, I will talk about a new method of doing Bayesian optimization. In our research lives, we often have to conduct black box optimization problem. We call certain system as a black box when the system is complex, so we can only observe input x and output fx. And it's optimization because we have to find a certain combination x star that optimizes fx. And this is happening when the objective function is hard to evaluate, so we can only observe the function value. We cannot observe gradients. For example, material searching, battery design, or AI hyperparameter tuning, lots of chemical engineering problems are often black box systems. So to find optimum point in this black box system, we have to do something called sequential decision making. What I mean by that is, based on a certain amount of data, we will make decision, and based on the decision, we will conduct next experiment, and based on the next experiment, we will get new data. And also, based on the data, we will make another decision. So this 3-step is being iterated time after time. And for a sequential sampling problem, to guide data-efficient decisions, we often use Bayesian optimization. And to guide this kind of data-efficient decision, Bayesian optimization iterates this 3-step approach. So the first step is surrogate modeling. Surrogate model tries to approximately understand, or in other words, model, the relationship between the input and output of the black box system. The most famous choice for surrogate modeling is Gaussian process model, because it provides both prediction mean and the uncertainty. In the next step, the user defines an acquisition function to decide which point to sample at the next time step based on the understanding of surrogate model. Expected improvement or probability of improvements are the most popular choices of acquisition function. And lastly, we conduct a real experiment and receive a new data. And based on this data, we'll update the model and we'll iterate the process from the step 1. However, the conventional acquisition function, such as expected improvement or probability of improvements, are criticized for acting myopic because they only care about expected improvement for a single decision, which means that those acquisition functions do not care about the future decisions. Therefore, it struggles to escape from the local minimum. However, in a real-world problem, we will almost never find a global optimum after the first iteration. We'll make one decision after the other and the other. Therefore, this entire process of Bayesian optimization can be seen as a stochastic dynamic programming problem. So we are at a certain initial state with certain amount of information, and based on the understanding, we have our choices of actions to make, and then they will probabilistically lead us to the second state, and same thing happens again and again and again. So by solving this SDP, we'll be able to find a perfect decision-making policy. However, this kind of SDP is computationally intractable because there are so many cases to calculate. So in 2016, to approximately solve this SDP, rollout-based Bayesian optimization has been introduced by Lamb in neural IPS. So rollout-based Bayesian optimization works like this. So rollout-based Bayesian optimization considers all the possible actions for the current time step. And it applies heuristic EI-based Bayesian optimization for the H-step lookahead. And after trying it again and again and again for all the possible choices, it chooses the action that shows the best total reward after the H time step. So this method tries to solve SDP in its own way, but we all know that it is not solving SDP in a near optimal way, because it only gives the freedom to choose at the first time step, but after that, from the second until the 8th decision, it only uses heuristic policy. On the other hand, reinforcement learning is a method that can solve SDP in a near optimal way. Reinforcement learning is a type of machine learning method that trains an agent by interacting the agent with the environment to find the best policy pi under a certain state. Based on this idea, this research suggests a method of BO guided by reinforcement learning. To train a reinforcement learning agent, a thing called Markov decision process MDP has to be defined. And MDP is a tuple consists of 5 sets. So the first element is the set of decision epochs. It means how many steps we will look for while making current decision. And also action space has to be defined. And action space can be easily defined because it is the search space, like where we're gonna experiment in the next time step. And state transition probability is defined in our system as a GP model because we already constructed a Gaussian process model. And also reward can be defined in a user-defined way. And it can be defined as how much improvement we're expecting compared to the current best point in our hand. However, the state space for the MDP was hard to define, like which state space are we existing at the moment. And we all know that RL agent has to understand the GP model we've constructed to do its recommendation. So I proposed a new set of state space. And my claim is that if we laticize the information of Gaussian process and provide it to RL agent, then he can understand what's going on in the modeling part. So let's say there's a two-dimensional GP drawn as, like gray and purple form. So the purple surface is the GP mean and the gray surface is the confidence interval of the GP model. And once it's a two-dimensional GP, we can laticize the input space into form at the right. And we can calculate what was the GP mean and uncertainty or standard deviation of each laticized points. And by integrating all of this into one matrix, we can suggest a new state space. So this is an abstract information of certain GP over certain action space. So now we've successfully defined MDP process for reinforcement learning. And to train AI, we have to decide which algorithm to use. And for this research, I used PPO, proximal policy optimization algorithm, to train the reinforcement learning agent because it is the state-of-the-art RL algorithm which shows a great data efficiency. And case studies are conducted in 3 types of benchmark functions because once we don't know how the real underlying function for our system might look like, we have to try if this kind of new optimization method works for several types of benchmark functions. So the ECLA function belongs to the many local minima type of benchmark function, and MATYAS function belongs to the plate-shaped benchmark function, and the sum square function belongs to the bowl-shaped benchmark function. So I let my algorithm to conduct optimization under certain functions and compare its efficiency with the other algorithms. And as a performance index, I use regret, which is the difference between the y-opt and the best data in our hand until that time step. And so the method of doing it is to choose random 30 or 20 fixed number of initial data from the search space and provide that information to expected improvement-based Bayesian optimization and rollout-based Bayesian optimization and reinforcement learning-based Bayesian optimization. They all receive same information at the beginning, but time after time they will recommend new points by their own policies. And throughout the experiment, each entities will not share information with each other. And throughout the experiment, its performance, in other words, regrets, will be recorded. And depending on the choice of initial points, the performance might differ. So the experiments was averaged over 10 experiments. So for a clay function, it was able to see that RL-based BO was outperforming EI or rollout-based Bayesian optimization when it's 3-step lookahead RL. And also for MATYAS function, RL was either best or the second best algorithm in terms of data efficiency. Also for the sum squares function, it was possible to see that RL-based BO was the most data efficient algorithm. And one extension that we can possibly do is changing the set of decision networks. Because in the chemical engineering industry, because of limitation of budget or time, we kind of have limitation on how many experiments can we make. For example, the total experiment number can be 10 until this project is over. In that case, it is kind of unoptimized to use fixed number of decision networks all the time, because when we are almost end of our research plan, then we have to focus more on exploitation compared to the exploration. So I suggested also shrinking lookahead horizon for the reinforcement learning. So for the first 5 to 6 experiment number, we will keep the lookahead decision network as 5, but after that, we will shrink it into 4, 3, 2, 1. So I compared it for Ackley function and sum squares function, because those two functions showed a huge difference between RL and the other methods. And yes, as you can see, until the 6th experiment, for both Ackley function and sum squares function, the efficiency for RL and SH stands for shrinking horizon. Both methods shows exact same efficiency. However, from the 7th until the 10th time step, you can see the shrinking horizon method shows better data efficiency because it focuses on the exploitation rather than exploration near the end of the experiment horizon. So yes, to conclude, RL-based BO can make data efficient decisions while solving STP in a near optimal way. And introducing an idea of shrinking lookahead horizon can be helpful when the experiment budget is fixed. And yes, this research was funded by NRF, and I would like to express my gratitude to Han Byun and my researcher, and my advisor J.H. Lee, and for their support. Thank you very much for your attention.
네, 좋은 말씀 감사합니다. 저희가 지금 한 선생님도 받으시길 말씀해 주십시오.
정말 또 잘 들었습니다. 좋은 결과가 나왔던 것 같고요. 한 가지 궁금한 거는 지금 제일 끝에 테스트 같은 경우에
네.
스캔하고자 하는 스페이스의 어떤 결정되는 바가 있는지, 그러니까 넓을 경우에는 더 성능이 지금 테스트한 것보다 더 서칭 스페이스가 넓어졌을 때 비슷한 효과가 나올 거로 생각을 하시는지, 아니면 처음에 이꼴로 갔던 스테이지 좀 더 길어져야 되는 거가 있다고 생각하시는지.
예, 제가 보기에는 그 서치 스페이스가 넓어질수록 이제 우리가 언더스탠딩이 더 스파르스해지잖아요.
네.
그래서 이 슈링킹 호라이즌을 도입하는 게 더욱더 의미가 있을 것 같은 게, 만약에 계속 그 5스텝 루커헤드를 굉장히 스파르스한 시스템에서 시켜서 한다면은 되게 익스플로레이션에 그 비중을 많이 줄 것 같습니다. 왜냐하면 언더스탠딩이 너무 작기 때문에요. 근데 오히려 스파르스 시스템에서 그 넘버 익스페리먼트가 스트릭하게 정해져 있다면은 뒤에는 최대한 빨리 익스플로이테이션을 더 중요시하라고 하는 게 더욱 의미가 있으실 것 같습니다.
그러면 하나씩 떨어뜨리는 게 아니라 스텝으로 2개씩 떨어뜨리는 거하고 비교를 해보셨을 것 같은데 어떤가요?
그 스텝으로 비교해 본 적이 없고요. 그냥 하나씩 떨어뜨리는 것만 비교했습니다. 그래서 이게 사실 진짜로 가장 이제 옵티멀한 폴리시는 만약에 총 익스페리먼트 넘버가 10이라면은 처음에 이제 10스텝 루커헤드를 하고 이제 다음 스텝에는 9스텝, 7스텝, 6스텝 루커헤드 어프로치를 해야지 이제 가장 옵티멀일 텐데, 근데 이 RL 베이스 비율을 이제 하다가 알게 된 것 중에 하나가 이 10스텝 루커헤드를 하나, 5스텝 루커헤드를 하나, 이게 큰 차이가 없다는 거였습니다. 왜냐면 데이터가 너무 없는 상태에서 너무 많이 같다고 생각을 해서 배우게 되면 오히려 의미가 딱히 없더라고요. 그래서 5스텝은 이제 거의 10스텝 어프로치랑 이피션이 비슷하기 때문에 5스텝 전까지는 계속 5스텝 루커헤드로 진행하다가 이제 마지막 5개를 남겨놓고 나서 이제 하나씩 줄여가는 방식을 택하기로 했습니다.
감사합니다. 감사합니다.
네, 감사합니다.
Alright, thank you very much for your presentation. I wanted to find out if there is any cost savings with the new approach, with the RL approach with the EI.
Yeah, so the data efficiency you see here is actually the cost reducted. So in this system, for example, out of like 15 experiments, we already found the global optimum of the system if you use RL-based BO. However, if you use like EI or rollout-based Bayesian optimization, although you conduct 20 or 25 experiments, you will never find global optimum of such function. So yes, this graph itself is the proof of the efficiency.
But how does that correlate with the computational time?
So when we use BO, actually computational time is much slower or cheaper than the real experiment. That's when the BO is useful. For CFD calculations or battery designing or polymer searching, each experiment takes up to a few days, up to a few weeks or month. So we can only sample one after one, like in a very sparse manner. So computational time for like EI or RL or rollout-based BO, it's all recommended within like a minute or two. So yeah, computational time for each recommendation is like negligible compared to the real experiment's duration. So yes, that's the important point here.
And then finally, the stepping at the end of the training
Mm-hmm.
for the RL.
Mm-hmm.
Is there any possibility of using, let's say, a non-constant gradient to be able to effect a better accuracy in your model? In your model, use a constant gradient, decreasing from a certain step up to the end.
Okay.
If there is a reduction from, let's say, 5 to, let's say, 3,
Mm-hmm.
and then another jump to another gradient, would there be any possibility for a much better accuracy? Or if there's any test like that?
So yeah, you're talking about like reducing the liquid horizon in a step function manner, but I think the real optimum is when you look 4 steps ahead when you have 4 experiments to conduct and 3 steps if you have 3 experiments left. So I think the step function looking liquid horizon can work, but I don't think it's gonna be much better or any better than just gradient minus 1 kind of liquid drinking horizon. And yeah, if you want, we can discuss more after the session.
예, 이제 발표 스케줄 때문에
네.
마쳐야 될 것 같습니다.
네.
예, 좋은 발표 감사드립니다.